That works.
In a previous discussion involving inverse functions, we discovered that if a function has a graph which is continually increasing or decreasing, then that function has an inverse which is itself a function. Now we, in the last section, discovered that exponential functions have graphs that are continually increasing or decreasing. For example, the graph associated with f of x is 2 to the x power is about like this, a continually increasing graph. And therefore, we know that the inverse of this function is itself a function. And we can even imagine its graph. We know that the graph reflects in the y equals x line, so we could even draw it here if we wanted to do that. We'll get back to the notion of the graphing in just a little bit, but let's go through the process of generating the inverse. We would write this as y equals 2 to the x, and for the inverse, we would just swap the role of x and y. We would write x is 2 to the y power. Now the trick would be to rewrite this expression so that y is isolated on one side of the equal sign. Well, at this point, we have no way of rewriting in that form. We have to introduce a new mathematical form called logarithm in order to complete this, this process. Now, logarithm allows us to rewrite an exponential form like this. We write this as y equals log base 2 of x. Now, it seems like everything is all jumbled up here for the time being, but let's concentrate on going from this exponential form to this logarithmic form. These are just two kinds of ways to express things, and if we understand the flow from one form to the other, we'll get started with an understanding of logarithm. All right, exponential form. Now, we know that 2 cubed is equal to 8, but the equivalent logarithmic form for this is log 8 base 2 is equal to 3. Now, just let's look at structure here for just a second. Now, notice the base here is 2, the exponent is 3, and the base here, the logarithmic base, is said to be 2, and the exponent appears over here isolated. So what we're seeing here is that the logarithm of a number in a certain base is equal to an exponent. A logarithm is an exponent. The world of logarithms is indeed the world of exponents. We are jumping into the world of exponents when we use logarithms. That's a very important concept to keep in mind all the way through this study of logarithms. Okay, now, an interpretation of this is this, that this stands for, or is a request for, we can even think of it like that, this is a request for the exponent on 2 that will give 8. That is, 2 to what exponent will give 8? That's what this is the request for. And that exponent is 3. All right, so this is the exponential form, logarithmic form. Let's go through a couple more. 5 squared is 25. So we write log. Now, the way you will remember this, or the way you will go from exponential form to logarithmic form at first will probably be a way that is based on memorization. And you will probably think about it like this. Now, we'll interpret it in just a moment, but here's how you'll probably memorize it at first. The notion is that in this logarithmic form, there are positions for 3 numbers. A number here, and a number over here. And this position contains a base, and that position contains an exponent. And this is the base exponent result right here. All right, so base exponent. So there are 3 items. One's a base, one's an exponent, and the other is kind of the result of the calculation. So base exponent, we identify base exponent, and then we write the kind of leftover number in this position. So that's a way to accomplish the logarithmic form. But it's really important to interpret the situation properly. We're thinking here that a logarithm is an exponent, and this really means the exponent on 5 that gives 25, and that exponent is 2. Okay, let's do one that has a variable involved in it. All right, for logarithmic form, there are 3 positions. Here's the base, here's the exponent. So when we go to log form, here's the base is 10, the exponent is x, and the number here is 7. So what this is this is a request for the exponent on 10 that will give 7. That is, 10 to what exponent will give 7? 10 to what exponent gives 7? You see the equivalency of the two. Let's go the other way. From log form to exponential form, just identify the base exponent relationship. Base exponent. So we have 4 to the third power is equal to 64. And for this one, base exponent. So 5 to the x power is equal to 125. Now, with this ability to go from exponential form to logarithmic form, we can simplify certain logarithmic expressions. Here, for example, log base 3 of 9. Now, we can accomplish this in a couple of different ways. We can just make a kind of an analysis here based on our understanding of logarithm. Logarithm is an exponent. And here we have a request for the exponent, which is applied to 3, which will give 9. That is, 3 to what power is equal to 9? Well, it's easy to tell that that is 2. Now, sometimes we'll easily be able to see through them, kind of like this one, and we can go immediately and say this is equal to 2. You see, or if we can't see through them easily, here's what we need to do. We'll set this equal to some letter, like n, let's say, and now we go from the log form into the exponential form to solve this. You see, and here's how it works. Base exponent, so we have 3 to the n power is equal to 9. And now the trick, the trick is to cause the bases on both sides to be alike. You see, we can write 9 as 3 squared. Now, when the bases are alike, you see, when in an equation, when the bases are alike, we can set the exponents equal to one another. We jump into the exponential world by using that technique. So bases are alike, n then is equal to 2. And if n is 2, this n is replaced with 2, you see. So we can even go up here and do this. This is equal to 2. So we're just kind of verifying what we thought before. Now here again, this is the idea that we want the exponent applied to 4, which will give 2. Now that's a little more difficult to understand. So what we might do is set this equal to a letter, and now go into the exponential form. 4 to the n power is equal to 2. And now the trick is to cause the bases on both sides to look alike. Well, 4 is really 2 squared. So this is 2 squared to the n. You see, and now power to power means multiply those exponents. So this is 2 to the 2n equals 2 to the understood 1. And now we can set the exponents equal to one another because those bases are alike. So we can say then that 2n is equal to 1. And dividing on both sides by 2, we find n to be 1/2. So the n here is 0.5 or 1/2. Now you might be thinking, well, gee, let's verify that. You may or may not be thinking about that, but let's verify that. Is it true that 4 to the 1/2 power is equal to 2? Is it true that 4 to the 1/2 power is equal to 2? You see, that's what this says. That's what this says. You see, and we found n to be 1/2. Is this true? Well, the 1/2 exponent is an implied radical, so this is the square root of 4 equals 2, and the square root of 4 is 2. And so we do have truth, and therefore this is correct. There are certain situations that occur in the logarithmic world from time to time, regardless of base, and we come to a conclusion about simplification very quickly. Here, for example, the log of 1, we can come to a conclusion right away if we just understand what this means. We have some base here, and I've not written the base because this situation applies to any base. Now, I can put one here for emphasis. I can say, okay, let's make it base 5. So log base 5 of 1, all right, is what? Well, let's analyze it the way we did before. Let's go into the exponential form. We have 5 to the n power equals 1. Now, this doesn't seem to help us very much until we realize that an exponent of 0, you see, on any base is simply 1. So this 1 can be written as 5 to the 0 power. You see, and with that, since the bases are alike, we set the exponents equal to one another, and n is equal to 0 right quick. So the logarithm of 1 is going to always be equal to 0. So the log of 1 is 0. And after all, it's kind of like, let's interpret it another way. We have a base exponent. We want the exponent on this that will give 1. And this could be just about anything we choose. Just make it a variable if you'd like. So what exponent applies to that base to give 1? And that exponent needs to be 0. All right, here's another situation that comes up from time to time. When the base here is the same as this number, it turns out that we can quickly come to a conclusion. You may already know what the conclusion is, but it's kind of like, well, this one's just so easy. Let's just interpret it directly. What is the exponent applied to 5 that will give 5? Well, it's simply 1, you see. So when this number and that one are exactly the same, the result is 1. Here's another one. Similar idea. I mean, we can interpret this one very quickly, but notice that we have log base 5 of 5 cubed here. Now, the interpretation is that we're looking for an exponent to apply to 5 that will give 5 cubed. You see, so all it is 3. And we can see it very easily if we set it equal to n, and we say 5 to the n power is equal to 5 cubed. You see, just go into the exponential form, and we immediately see that n needs to be 3. So when you see this base of the logarithmic form and the base of this exponent as being alike, then the number just pops in right here. That's all. So n is equal to 3. Here's another situation that occurs from time to time. If we have a single logarithm on both sides of an equation and they have the same base, then we can actually set these numbers equal to one another. This must be the case that x is equal to 5. And if you think of logarithm as another operation along with the operations from arithmetic of adding, subtracting, multiplying, dividing, then we have exponentiation, and we have absolute value, and we have radicals. This is just another operation, let's say. Now, all of those operations, or many of them, have inverses, have undo sort of operations. And if we think about undo logarithm on both sides, we see undo logarithm on both sides, then we would have x equals 5. Just kind of a convenient way to look at that situation. Okay, consider this one. Log base 10 of 1,000. Our interpretation in terms of exponent would be, what is the exponent we need to apply to 10 in order to get to 1,000? Well, it would be 10 cubed. So this is equal to 3. Now, we can make that determination using this, setting it equal to n if we want to, and going through that little algebraic process, but I think it's easy enough to see through. But my point here is this, that the base 10 in logarithms is such a common base. It is called the common logarithmic base, and it is the base of logarithms found on the calculator. There are actually 2 logarithms that are on the calculator that are just default within the calculator. This is one of them. We'll talk about the other in a minute. But because it's on the calculator, we can make the calculation for the log of 1,000 using the calculator. Now, a lot of times this 10 is not even written. If a logarithmic base is unwritten, then it's understood to be 10. So this might be shown as log 1,000. And to make the calculation on the calculator, you do this. You press the button marked log on the calculator display, enter 1,000, and press enter. Now that's what you do on graphing calculators. On scientific calculators, logarithm is one of those immediate response functions. You know, you don't even have to press enter for it, but you press the 1,000 first, and then you press the log button, and it'll give you the log of 1,000. Well, at any rate, what should come out of this is the number 3. Now, for this one, once again, we could use the calculator to make the calculation. Let's also go through the algebraic form here. Let's set this equal to some letter like n, and then set up our exponential form. Now, the base here, since it's unwritten, is understood to be 10. So this is 10 to that exponent is equal to 1/100th. 1/100th. Wow. How do we make the bases on both sides look alike? Well, we can do it like this. We can write this as 1 over 100, and 1 over 100 is 1 over 10 squared. and we can kick this 10 squared up into the numerator by applying a negative exponent. So this is 10 to the n is equal to 10 to the negative 2. Aha, so n then is equal to negative 2. So this then is negative 2. Now, the interpretation is this, that negative 2 is the exponent that needs to be on 10 in order to give 100. And if you look at it algebraically, sort of, then it turns out pretty easy. But using the calculator now, remember, here's what we need to do. We would press log, pump in a 0.01, and then the enter, and then we should get negative 2 as a result. Well, there's another commonly used logarithmic base, and that base is e, it turns out. Now, we studied about the naturally occurring constant e when we talked about exponential functions. And actually, you know, when I mentioned to you about the significance of e as the base of an exponential function, I kind of implied, and I'm telling you here, that it is the most commonly used exponential base. And it is probably the most commonly used logarithmic base as well. So this e business has a lot of significance here, and it adds a great deal of power to our mathematical toolbox. Now, because it appears so often, it also has kind of a default aspect within the calculator, and it has kind of a nickname. That we know that log x, if no logarithmic base is written, then it means log base 10 of x. We know that. But on the calculator, ln x, there's an ln button on the calculator, and that means the natural log of x, which means the log of base e, the log base e of x. Okay, so log base e of x means the same thing as ln x. Now, all of our rules, all of our little things that we went over here involving logarithms, regular logarithms with bases other than e, apply to natural logarithms. So we have, let's see, ln1 means log base e of 1. Remember what that was? We're looking for the exponent on e that will give 1. Well, that exponent needs to be 0. And here, ln e, well, that just means that we have log base e of e. You see, and when the logarithmic base is the same as that number, the number here is 1. And again, ln e to the fourth is simply 4, because we discovered that this is log base e, you see, of e to the fourth power. And this is a request for the exponent on understood e that will give e to the fourth. What exponent needs to be applied to that e? Well, a 4 does, you see. So we just read it off like that. Now, once again, since this is a logarithmic base that is found in the calculator, we can just punch the calculator to make the calculations for natural logarithms. If we want ln 7. Now, what we're calculating here for is the exponent on e that will give 7. That is, e to what exponent gives 7? And that exponent turns out to be 1.95. And we find it by pressing ln, and then 7, and then enter, and we get approximately 1.95. Now, this is a very long decimal. It's an irrational number, so I've rounded it to this value. And also, ln 25 turns out to be 3.22. You might try this on your calculator just to get a little practice with it. But remember, what this means is we're looking for the exponent on e that will give 25. That is, e to what power is 25? Well, e to that exponent will give 25. And actually, it's e to approximately that power because it's a rounded number. Let's look at the graphs of some logarithmic functions. And we'll do this from the perspective that they are inverses of exponential functions. Now, earlier, we generated the inverse of this exponential function. We know all about its graph. Its graph is right here. The inverse we found to be y equals log base 2 of x. And we can designate that as f inverse of x, then, is log base 2 of x. Now, we know over here that we have a graph, then, of this logarithmic function that is a reflection in this y equals x line. So it'll be a graph that will make its appearance over here. Now, if we were going to generate a table of values for the construction of the graph, we could do that, but using our calculator would be a little difficult because we have a logarithm in base 2. And right now, we don't have a way to use the calculator to calculate the logarithm of numbers in base 2. We'll learn about that in a little bit, but we don't know about it right now. But there is another technique that we can use, and it's the technique of using the notion of that inverse idea. That is, I have a table of values here associated with the exponential function. And that's these points were plotted to get this graph. All right, all I have to do to generate the graph of the inverse is to simply swap the role of x and y here. So I can make a table of values for the inverse function just by taking the x column here and writing it as the y column, and the y column here and writing it as the x column here. And then plot the points. 1/4 goes to -2. Well, let's see. An x of 1/4 goes to -2. 1/2 goes to -1. 1, 0. 2, 1. 4, 2. And 8, 3. And the graph. And this is about what we would expect. Now, notice also that we started with this exponential function whose domain is, well, let's see. I'm going to write the domain and range of that function. We want to investigate those ideas as well for the logarithmic function. So the domain for our exponential function, the acceptable replacements for x algebraically or graphically, it's for what values of x do we have points on the graph? Well, for all values of x, we have points on the graph. So the domain would be all real numbers. I'm going to use this designation for the set of real numbers. How about range? Well, the range, the y values that are on the graph. For our exponential function now, the y values would be the y values that lie up here. None of these y values have x partners that put points on the graph. So it's just y values that are distinctly positive, because a y of 0 doesn't appear on the graph either, because we have an asymptote at the x-axis. So it would be y values that are greater than 0. Now notice what happens with the logarithmic function. The roles of the domain and range are simply swapped. So for domain, for the logarithmic function, the domain is, let's see, for what x's do we have points on the graph? Well, for all of these x's that are positive, we have points on the graph. So it would be x greater than 0. What about range? For the range, it would be, let's see, for what values of y do we have points on the graph? Well, for all values of y, we have points on the graph. Even for the y's up here, the x coordinates for y's that lie way up here would be way out that way. But at any rate, they do exist. So the range would be all real numbers. Now, also, the asymptotes have kind of swapped positions in a sense as well. They have actually reflected in our y equals x line too. And we can't see them because they are the axes that are on our graph. They are the axes for the coordinate plane. But the x-axis is the asymptote for our exponential function, and then when we do this swap around, this reflection, turns out that the y-axis is the asymptote for our logarithmic function. Well, we can examine the graph of the whole family of logarithmic functions by using this approach that these functions are inverses of exponential functions. For example, we might want to look at the shape of the graph of log x. Now, that's log understood base 10 of x. Now, it's inverse. Think about it now. If we're thinking we want to graph log x, that's y equals log x. What's the exponential form? Well, the exponential form is y equals 10 to the x power. And 10 to the x power as an exponential function now would be a graph that goes up really sharply right here. And so that graph would kind of look like this and come down and get really tight on the x-axis, and away we go to the left. Well, its reflection in the y equals x line would cause a graph like this to occur. It'll be actually pretty tight on the x-axis, and then it'll come right over to the y-axis and down in a rather big way. So it kind of makes a sharp shoulder here. So that's the graph of log x. Now let's use that. Let's use the graph of log x and talk about some transformations. And it turns out that all of our ideas about transformations work just as well with logs as they did with exponential functions, as they did before with other kinds of functions. But let's just go through the process again. We have a prevailing operation here, and it's called logarithm. And we're talking about adding or subtracting before applying the prevailing operation or after applying the prevailing operation. If we add or subtract after the prevailing operation, we know that the movement of the graph is up or down the coordinate plane. If we apply the adding or subtracting before the prevailing operation, we move left and right in a direction we don't expect. So we start with the idea of the graph of y equals log x. And then from that we make our transformations. Consider y equals log x plus 2. So it would be these vertical distances, then plus 2. So take all these vertical distances, lift them up to, the graph appears then to just rise 2 places. And I'll just move this nice point here, this nice reference point, and all the other points follow, and here then would be the graph. For this one, we are adding 3 before applying this prevailing operation of logarithm. So the movement is left or right in a direction we don't expect. We see plus 3, so the graph is going to move to the left 3. So from this position, it'll move over 1, 2, 3. So that point moves to this position. Now, when you move left or right, it's important to move the asymptote as well. The asymptote was at the y-axis, so it'll move over 3 positions, 1, 2, 3, and here's the asymptote, and the graph then would look about like this. What about this one? We have a couple of transformations involved. Let's consider this one first. The x minus 1, the subtraction of 1 before the prevailing operation of logarithm. We move left or right in a direction we don't expect. We're thinking, well, let's see, minus 1 moves to the right 1 on the coordinate plane, so we move to this position. So here's the graph. Now, since we moved to the right, the asymptote moved over to the right as well. So that rascal moved to here. Now, what about the negative of this? It's the negative of all of these vertical distances, you see. So that causes the reflection in our x-axis. So that rascal flips over, and this business right here will appear below the x-axis, and the business down here will appear above. And so the graph then will look about like this. Something like that. Here's another one. Y of log negative x. Now, we're looking at reflections here, and this is a distinct reflection, and there's often confusion on the part of students as to whether or not we're reflecting in the x-axis or the y-axis. Now let me review something for you here. If we have f of x is log x, we know what the graph looks like. Now, the negative of f of x means negative log x. It's the negative of all of these vertical distances. Oh, that's the one where we reflect in the x-axis. You see, that's the one where we reflect this way. That's the one that's easy to see. F of negative x, though, is the log of negative x, and that's the situation we have up here. And that's the reflection in the y-axis. So we're reflecting this way and not this way. All right. So we're going over here, and then let's see. This point moves over to here, and the graph then looks like this. Okay, that's the idea. This negative sign here brings to mind something that we need to mention. You know, we said that the domain of a logarithmic function would be all positive numbers. X is greater than 0. We can see it graphically, we can kind of see it algebraically, but I want to emphasize it here with a little manipulation. Why is it? Why is that the case? Well, it's the case for a number of reasons, but it manifests itself in a situation where we try to take the logarithm of a negative number, and it turns out that we can't do that. Let's see why we can't do it from the perspective of an exponential equation. You see, suppose we try to take the log of negative 4 in, let's say, base 5. The base really doesn't make any difference here, but it's the idea that we set this equal to x, and then we have, in exponential form, 5 to the x power is equal to negative 4. And so we're looking for an exponent to apply to 5 that will give a result that's negative. You see, now although x can take on both positive and negative values, it's never going to cause this expression to become negative. So this is an impossibility. We just simply can't take the log of a negative number. Now, since we can't take the logarithm of a negative number, that leads to some restrictions on the domain of logarithmic functions. Now, we said that basically log functions, log x, you see, log base 10 of x, log base 2 of x, those kinds of things have a domain which is easy to establish from the reflection of exponential functions. All right, but let's do it from a different perspective here. Let's think, well, okay, we can't take the logarithm of anything but positive values. So to establish the domain here, we'd like to know the values of x that will cause x plus 3 to be greater than 0. You see, and subtracting 3 on both sides, we find x to be greater than negative 3. So x is greater than negative 3. And we could kind of see this if we construct a graph of this, and we could do that with transformations. You know, we could take that basic graph of the log function and then shift it over to the left 3 and see that we have x values on that graph that are greater than negative 3. That's another way to look at it. But I kind of like this algebraic approach as well. Consider this one. Now notice that this is a natural log function, and all of the aspects of log functions for any base apply to natural log functions, because after all, this is just a logarithm in base e. So it's really not any big deal. The shape of the graph is pretty much the same as the shape of the other. And domain and range, same idea here. Okay, let's talk about domain. The domain is found by kind of saying to yourself, well, we can only take the logarithm of positive values, so we'd like to know the value of x that will cause 2x minus 3 to be greater than 0. So we add 3 on both sides, divide by 2, whoops, not equal, greater than. So x is greater than 3 over 2. X is greater than 1.5 then as the domain of that function. Now what about this one? Now this one is kind of interesting from a graphical standpoint as well as from an establishing of the domain standpoint. Now if we're finding the domain, we want the values of x that will cause this value to be positive, because we can only take the log of positive values. So we want to know what value of x will cause 3 minus x to be greater than 0. If I subtract 3 on both sides, I get this. And then if I multiply on both sides by negative 1, I'll clear the negatives. But I also need to change the sense of the inequality, because I'm multiplying in an inequality by a negative number. So this is x is less than 3. X is less than 3. All right, now what that tells us about the graph basically is this, that if we don't know anything else about the situation, we know this much, that at 3, for x values less than 3, the graph is going to lie over here, and the asymptote is going to be here, you see, for x values to be less than 3. So we're over here with our graph. Now, how does that graph behave? Does it do this? Does it do that? How does it behave? Well, that's another matter for consideration. Now, we might try to go through the process of thinking about transformations using the information here, but this is pretty tricky. This is a very tricky situation to deal with transformations. Tell you what, let's look at it on the graphing calculator. Here's our function, and the graph has the expected kind of behavior. Now, to verify the calculated domain of x being less than 3, we can sort of see it from looking at the calculator display here. Here's a tick mark at 1, and then 2, and here's 3. And it appears that the graph makes its appearance on the coordinate plane for x values less than 3. Well, to verify that further, using the trace button, we can trace over and get near 3. Let's see, as we come near 3, notice now I'm at 2.8, 2.9, and when I cursor over to 3, there's no definition for y. So and the x's are defined for only values that are smaller than 3, as we expected from the calculation of our domain.